Hey guys, so this is the third and final part of the RP20 evaluation board series. What I'm going to cover in this video is first the exporting of the Gerbers, a kind of final checklist that I do, and a couple tweaks you can do before uploading to a PCB fabricator. Once we get through that, I'll cover how I paste the board, how I put the stencil and the solder paste on the board, how I place all the components, and then what I did to reflow this board, and I'll mention a few alternatives that you can also do instead. Once the board is fully assembled, I'm going to spend a little bit of time going through some testing and some programming on the board just to make sure everything is fully functional and we don't need any hardware changes on the next revision. So with all of that said, let's jump into the PCB. Okay, so the PCB here is actually the second revision where I made a couple hardware tweaks already. I wasn't doing a good job on version control and version revisions, so I don't really have access to the original one, but it's fine. The only thing that I made changes on is just shrunk the board east and west to make it fit a breadboard better, and then a little change to the I2C bus, which I will mention later in the video. And then what I mentioned in the last video is just adjusting the labels for the RGB LED, just so it followed what the schematic was on. Other than that, it's completely the same and nothing has changed. So the first thing I like to do when I'm getting ready to do a Gerber export is obviously you want to run a DRC check and make sure that makes sense. And it doesn't matter always if there is some errors, they just have to make sense. So for here, there are a few silkscreen errors from it being cut across the board, and that's totally fine. That just shows where the PCB is going to, or the connector is going to sit. And this should be probably a drawing layer instead of silkscreen, but I usually just keep this because if it's on a panel, it kind of designates it. So I'm totally fine with that. My mounting holes, I don't know why. I think I mentioned this in the last video. It shows that there's a double drill hit, but on the Gerber export, it won't matter. So that is fine because it shows double there. So I need to just edit the mounting hole. But for now, it's fine. And then unconnected items, I am not connecting these shielded pins together, but it's only a single shielded pin on the schematic, which is fine. So I can ignore all of those, and you can add a custom rule to basically ignore those, but I honestly never find it worth my time. So once the DRC is done, then you know that there's nothing obvious that is an issue with this. The next thing that I like to always do is put on the mask layer and just have a look at the board and make sure nothing like jumps out. So when I say jump out, sometimes when I export a footprint from my footprint tool, sometimes it'll just have an outline of the mask in just a line, which obviously is not good. So I like just doing like a quick visual check of all of the parts, make sure what is solder mask should be. And just as a quick reminder, remember everywhere you see solder mask shown is where there actually will not be on the PCB. It's a negative, just because the majority of a PCB inevitably has solder mask on it, and make sure that fiducials don't have solder mask. So with a quick look there, everything makes sense. And now the only real setting that I change for exports is on the solder mask and paste. I make the solder paste absolute clearance negative 0.5 millimeters. And what this does is when you check on these paste layer, and again, this is something I did mention in one of the other videos, but I just like to cover it again. What that does is basically shrink the amount of paste that will be on the PCB, and it has a few benefits. One is simply it it reduces the chance that there's going to be solder balls just because there's less paste. It also makes it so if your stencil isn't perfectly aligned, say if it's off by 0.05 millimeters, it's going to still be just on the exposed copper, which is obviously good. And the third reason, I'll pull up this picture to help show it. So the black is the stencil, and the area here is where the aperture is. The green is your solder mask, and then the yellow or goldish is where the actual copper and the plating is. And of course, since the solder mask is applied above the copper, it's a little bit of height, and that's where your paste drops down into. The top one here is where the aperture is reduced, and the bottom one is where it is the standard same size as the opening. So you can see two things in this top picture. One is you can see that little wiggle room where the paste has leeway. If it's not perfectly aligned, it's still going to be deposited in the little opening. Whereas on the bottom one, any misalignment means paste is going to go on that edge. The other thing it shows is since it actually drops within this space, it makes a perfect gasket and seals the edge of the opening. If you make it the exact same size, unless it is perfectly aligned, which isn't possible, you're always going to have a little bit of leakage right on this edge to where it can seep up under here. Where over here, you've got this whole opening space to where when you do, let me draw this, where when you do your paste and it comes down, a little bit's going to go back here, but there's not going to be any pressure to force it up under here. Where on this one, since it basically fills this entire channel, especially if you do a second pass, it's going to have pressure to push it up under here and leak out. So whenever possible, you want to go ahead and do that. Now, there is one slight gotcha to that. It's not specific to reducing the aperture size specifically, but it is exacerbated with that. So there's a formula that you don't see a lot of people, at least in like the hobby field, kind of bring up, and it is probably the cause of a lot of issues when people are stenciling. So it's called the aspect ratio of a stencil, and it's simply the width of the aperture divided by the thickness of the stencil. And for the width, that's really just the minimum length side, since if you were to do this length, it's obviously going to be bigger, and the whole goal of this is to make sure the aperture is big enough, so you always take the smallest side. And what the aspect ratio does in the real world is if it is smaller than 1.5, when you go and paste through this, so you do your paste, when you lift the stencil up, it's going to have enough surface tension to where the paste stays in the aperture. So you pull up your stencil and all the paste, or at least part of the paste, stays in the stencil and it doesn't get deposited on the board, which is, for obvious reasons, a big issue. Now, there's ways in which you can mitigate it, and the biggest one is to get an electro-polished stencil, which that smooths out these edges so it makes it to where it won't stick as easy. And then you can also get some hydrophobic coatings on it to make this edge slippery. But even with that, you always kind of want to follow this golden rule. So when that's put into practice, I almost always will use a 0.12 millimeter stencil, and when you divide or multiply that out, it gives us a width of 0.18 millimeters. So the rule of thumb that I'm using when I'm designing and working on pretty much any board is the smallest edge of any aperture needs to be bigger than 0.18 millimeters. And if you notice on the RP2040, I don't have the full stencil reduction like I do on all of the other parts. And there's a reason for that, and that is because I have overridden the absolute clearance for all of these pads. Because if I don't, and I let the 0.05 reduction occur, that makes my aperture 0.1 millimeters, which is clearly less than 0.18. So if I didn't do that, and I went and stenciled this, unless it was a really high-end stencil with a electropolished finish and the hydrophobic coating, I'm not going to get much paste on here. It's all going to stay within the stencil. So instead is you'd go to the clearance overrides, and I do this per the part library footprint, not per the individual board, just because, like I said, I use the same thickness stencil for almost all of them. So by changing that and making it to where it is, in this case, negative 0.01 millimeters instead of using the global, and let me reduce down my grid to where I can measure it, it is now 0.18 millimeters, and it should remove from the stencil perfectly fine. And once I've gone through the board, checked all of the paste apertures and everything looks good, it is then time to start actually exporting the Gerbers. And the first thing to do is set the output directory to whatever you're going to use. I'm not actually going to export this, so it doesn't matter. On the default plot settings, it is pretty much bog standard. At least it is on the latest versions of KiCad, so I'm not really going to go through. You can check what I have if you want to adjust yours. The important layers are all of your copper layers, of course. Don't worry about the adhesive. That's only if you're using an adhesive layer for gluing the parts to the board. If you have a bottom paste layer and it's a double-sided board, you can check that. If not, don't check it. The silk screen, again, if you only have front silk screen, check that. Leave this one unchecked. You always want front and back masked. You rarely need user drawings. User comments is common if you're using a panel. So if it's a panel, check that. Eco layers you don't normally use. Edge cuts you always have to have. That's obviously the border of the PCB. The margin, courtyard, fab, all of these you rarely use. So you leave it basically just like this. The only adjustments are if it's a double-sided board, if you have silkscreen on the bottom, and then if you are using a panel. Other than that, you keep it pretty much like this. So you will plot that and then go to generate drill files, which again, this is the standard format that it's in, and it works for pretty much all fabs. And you hit generate drill file, and now you have a project or a folder that has all of your Gerbers in it. And I'm not going to go into any specific uploading procedure for any fab because with the settings that this board has, it's all pretty much identical and it would just be kind of redundant. But you just take the Gerbers, upload them to whatever site, and you should be good to go. So the method for applying solder paste I'm using is kind of rudimentary. So I tape down a dummy PCB of the exact design that I'm using first. Then using double-sided tape, I attach a second board, which will be the good PCB. And I have to use a framed stencil for this method, which I honestly think is a no-brainer. It's not that much more expensive. And then I just attach the stencil on top using simple woodworking clamps, apply the paste on. I'm using a ProFlow cartridge, which you don't have to mix the paste, but I find that it works really well, or it helps it a lot to do that. And doing it with the frame stencil like this, I honestly do it all the time. I've done it down to 0201s. I've done a 0.5 millimeter pitch BGA. As long as you align it well, it works really, really well. And the reason I like it is it's super quick to set up. And since we do a lot of prototypes, you can literally set this thing up without a jig in, 60 seconds flat. And then from there, just pop the PCB off and you're off to the races. And it probably comes as no surprise I just hand place all of the parts using tweezers. I do have a vacuum pump tool that I'll use for like really big ICs, like if it's a big microcontroller or something like that. But otherwise, I find it pretty quick to just use tweezers. So while this is playing in the background, I'll talk about how I reflow boards. So I've done a couple videos or live streams where I talk about it. And it's basically just a custom aluminum plate that has 6 cartridge heaters inside it. And it just acts as a super high power hot plate. And I was going to do a full video on it, but honestly, for most applications, especially for hobby use, it honestly just makes more sense to go to a grocery store or on Amazon and just buy a off-the-shelf hot plate and then put a aluminum plate on top of it to help diffuse the heat. And that's what I used for a couple years until I went to this, and now you can see it obviously reflowing on the screen. And as long as it can heat it up fast enough, or you start it with a little bit of extra heat, it usually works out pretty good. And if you don't have a hot plate, then just using a standard hot air gun works pretty well. And then for soldering the pin headers, it's pretty easy. Just place it in a breadboard, solder everything on. And I didn't have thermal vias for the 2 ground pins, so they were a bit of a hassle to solder. You'd kind of want to preheat it to make it a little bit easier, but overall not too bad. So now that the board's fully assembled, the next step is obviously to test it. And since this is just an evaluation board, there's not a ton to test. We of course want to make sure that the Pi microcontroller, it's talking to the flash. We want to make sure that the USB going to the Pi is routed and that is correct. Nothing with the TVS diode just screwing anything up. Make sure that the voltage regulator is fine, the RGB LED is working. And then for the connectors, short of testing every single one individually, which honestly is just going to check a soldering mistake, we really just want to maybe check the I2C bus here just to make sure that that connector is working. And that's pretty much it. And of course, by doing this, we will know if the oscillator is working or not. And the first thing when you go to power a new prototype on, I like to do is put it on a current limited supply to make sure you're not going to blow it up, which I have already done, and I did that just by powering it in on the 5-volt input. And for the sake of this video, I'm not going to bother going through that. I'm just going to plug straight into the USB connector, but just keep that in the back of your mind. That's normally a good practice just to help protect the board that you just assembled. So for doing this, just a big disclaimer, two things. One, this is the first project I've ever done with the RP2040, so I don't know a great tool chain or anything on the programming side or the software side. Second, I do not do embedded firmware anymore. I have people who do that for us at work. So I'm just going to be using MicroPython through Thony, which seems to work good enough just for testing. To state the obvious, if this is something in production or you're doing it for any sort of higher performance application, you of course won't want to run Python on it and just run straight C or C++, but for this it should work fine. So the first thing you want to do is of course just plug in the USB, and it won't show up as a mass storage device right off the bat. We need to put it into boot mode, and for this board the boot pin is the button closest to the USB connector. So you hold that and then just press and release the reset, and it'll show this mass storage device, and you could drag on just a UF2 file to it. But since we want to use MicroPython, we go to on Thony, go to the interpreter, install or update, hit just the generic Raspberry Pi Pico, hit install, and once it's installed, just hit close, hit OK. And as long as when you hit reset and then hit the stop restart, it should connect. I do not know why it is not. Let me go to the interpreter. The port needs to be detect port automatically. So now we should see the shell, and that means that it is able to run locally the Pi interpreter and then send it over to the Pico or the RP2040. And I have a couple just simple scripts made up to test the RGB LED and then scan for an I2C, or scan for I2C and then actually talk to the sensor. So for the RGB LED, it's pretty simple, just RGB for the 3 pins, set the duty cycle to 0, 1 kilohertz, and then in sequence just 0 to max brightness RGB. So if we run that, you should see the RGB go all the way through red, then green, and then blue. And just a real quick side note, if you haven't used MicroPython before, this isn't actually running it directly through or saved to the microcontroller. So if I were to disconnect, hit reset, it no longer is running that code. If you want to have it be saved on there, you explicitly have to save it to the RP2040, save it as main.py, hit OK. Now we disconnect and can do a reset, and now it's running it on there. You don't have to be connected to the computer. But for just testing and doing development, I assume you're not really going to be doing that and just going to be running everything through the IDE. So now we know that the I2C, or now we know that the RGB LED is working. We also know that pretty much everything on the board is working, because in order for it to do that with the correct timing, everything down here has to be functional. So truthfully, the I2C test is just kind of for fun. So I am using a temperature and humidity sensor, the AHT20, and unfortunately on the first revision of the board, I didn't realize that the connectors or the cabling for the Stemma QT connectors are actually inverted. So the pinout was flip-flopped. It's correct now, but on the board over here, it is not. So I'm going to have to connect the sensor to the pin headers, which I will go ahead and do right now. Okay, so now the sensor is attached to the headers just like I said. So now if we open up the I2C scanner, this essentially just using the pins we have will run through all possible addresses on that bus and see if anything pings back. So when we go and run it, we see, as you would expect, one device with an address of 38. So we know that it is on the bus, which again, we would expect because there's nothing really here to not work. So for the final test, I'm using just an open source library by these authors. And instead of just importing it as a library, I just threw it on the main file and created the class instance from it and just print out the temperature and humidity. So if we run that, if we run that, apparently I typed in something on accident. And if we run that, the temperature comes up 20 C and 39% humidity, which sounds reasonable for me. And if I put my finger on it, you would expect both to skyrocket, which they are, because apparently my hand is clammy and it is quite hot compared to the 20 degrees. So that pretty much shows that the I2C is working, and it shows once again that everything on the evaluation board is functional other than just needing to correct the pinout. So that pretty much wraps up not just this video, but also this series. I hope I was able to explain everything going from the schematic to the PCB to the assembly and now finally the testing. I could maybe, and let me know what you think in the comments or in Discord, I could maybe do like a EMC video on this, kind of checking the ESD diodes, checking some EMI. But honestly, it's such a simple board, I don't think that you would really get much out of it just because there's not much going on. But of course, let me know. As always, I hope you guys enjoyed, and I will see you in the next video. Have a good one.